Okay, today we'll study some examples of linear ordinary differential equations. Now we consider the first example. Suppose Pi is some continuous functions, and then we have a differential operator Ly sigma I from 0 to n Pi, the i's derivative of y. Okay. Then, if phi is a non-zero solution of this homogeneous nth ordered differential equations, then our conclusion is that all zeros of phi are isolated. Okay, so in the last lecture, we have studied the second order case, that is n equal to 2. But now we will study the general higher ordered ordinary differential equations. So this problem seems quite difficult. Actually, this is a very interesting problem, and I have posted this problem on Skype for you to view before watching this lecture. Okay, so but I believe most of you don't know how to prove this interesting conclusion. Let's see what to tackle this problem. So firstly, we need a calculus result. That is, if f is case-ordered differentiable and it has k plus 1 zeros in some open interval AB, then we have this interesting conclusion. There is a point in the interval AB such that the case-ordered derivative of f at this point C is 0. Okay, this is an important result, and so let's have a look on this picture. So the black dot represent the zeros of f. Then between any two black dot, that is f is 0 on these 2 points, this point and this point. Then by the Rolle theorem in calculus, we know that there is a zeros of the first order derivative of f. The blue dots are zeros of f prime, the derivative of f. This is a consequence of the Rolle theorem. I'm sorry, here there is a misprint. The blue here should be zeros of f prime, not f. I copied the words here, and I forgot to add the prime. Okay, so we have so f has in this picture f has 1, 2, 3, 4, 5. F has 5 zeros. Then applying the Rolle theorem between any two continuous zeros, we obtain the 4 zeros of the derivative of f. That is these 4 blue dots. Okay, then we apply the Rolle theorem to the derivative f prime again. We obtained between any two zeros of f prime, the derivative, we can obtain 0 of the second order derivative. Therefore, applying this argument again and again, eventually we will find the zeros of the higher order derivative of f. So this is the idea. So this is a result in calculus. We will need this result to prove the conclusion of this example. Okay. So let's suppose tau is a zeros of phi. So we declare that there is some k less than n, so that the case ordered derivative of phi at tau is not 0. Okay. Otherwise, if all the derivative of phi up to order n minus 1 at the point tau is 0, then the phi is a solution of this initial value problem. If our this conclusion is not true, then our phi is a solution of this initial value problem. Okay. Then obviously the consequence function y equal to 0 is also a solution of this initial value problem. So by the uniqueness, we conclude that phi is identically zero. So this contradicts the assumption that phi is a non-zero solution of our homogeneous equation Ly equal to 0. So this proves our claim that there is some k, so that phi k tau, the case ordered derivative of phi at tau, is not 0. Now, by the continuity of the case ordered derivative, because the derivative is not 0, we might assume that it is positive. The argument is the same for the negative case. So suppose the derivative is positive. By the continuity of phi, we can find some delta positive, such that in the delta neighborhood of tau, the case ordered derivative remains positive. This is a consequence of the continuity of the case ordered derivative. Okay, so now we want to prove the zeros of phi are isolated. So we argue by contradiction. If tau is not an isolated zeros of phi, then in this small neighborhood of tau, we will have infinitely many zeros of phi in this open interval. Now we can apply the calculus result we discussed at the very beginning. We conclude that the case ordered derivative of phi at the point tau is 0. There is some point in this interval. There is some point c in this interval, such that the case ordered derivative of phi at this point is 0. So this is a contradiction, because previously we have concluded that the case ordered derivative is not 0, is strictly positive in this interval. Okay, but if we assume that we assume that tau is not isolated, the zeros of phi tau is not isolated, then we will obtain a point in this interval such that the case ordered derivative is 0. So this is a contradiction. Okay, so this contradiction proves our result that any zeros must be isolated. Okay, so this argument is very clever. The nth order case is much difficult than the second order case n equal to 2. For the case n equal to 2, then this k is 1. So phi prime tau is not 0 means that phi prime tau is positive or negative. Then phi itself is strictly increasing or strictly decreasing. Therefore, tau will be the only zeros of phi in a small neighborhood. Okay, so the second order case is very easy, because when n is 2, this k can only be 1. So phi prime tau is not 0 means that phi is strictly increasing or strictly decreasing in a small neighborhood. So 0 is the only tau is the only zeros of phi in the neighborhood. Therefore, you can compare the argument for n equal to 2 and the general n. The general n, to prove the general n case, you have to seek help from this calculus result. Okay, so differential equation will use a lot of calculus technique analysis. So this you should pay attention to this. Okay. Now we consider the next question. Here we are required to solve this variable coefficient linear second order no homogeneous differential equation. We know that for linear differential equation, if the coefficients are constant, we can always solve the equation. Okay, but for variable coefficient case, here our coefficient of y double prime is x squared. The coefficient of y prime is minus 2x. These coefficients are variables, so we have no general idea to solve this equation. But to observe this equation, we will. It seems reasonable to find the solution of the power function y equal to axk. It is reasonable to find the solution of this form. Why this is reasonable? Because if y is a power function xk, then the derivative of y is a k minus 1, xk minus 1. But you multiply an x here, so this is also this term is also xk. Okay. Similarly, the first term, if y is some axk, then the first term is still xk, because y double prime is xk minus 2, but now we have an x square multiplied in front of y double prime, making this term xk also. So it is reasonable, flexible to consider whether this equation has a solution of this special form. Okay, we can try. Therefore, we substituting this function into the equation and calculate. Okay, 2x cube is the right hand side of the equation, which will, if y equal axk is the solution of the equation, then this equality will be true. Now, this derivative is very easy to compute. And computing the derivative and grouping the terms together, we will see that the result is axk k squared minus 3k plus 2. Okay, so from this equality, the question becomes whether there is suitable a and a k, so that this right hand side is precisely 2x cubed. So you want this equality to be true, k must be 3, because the left hand side, the power of x is 3. Therefore, on the right hand side, the power of x, that is k, must also be 3. So when k equals to 3, you can compute k squared minus 3k plus 2. This is 2. So k equal to 3, a equal to 1. Make this equality true. Okay. Therefore, we take a is 1 and k is 3, and then the equation y, the solution, the function y equal to x cube is a solution of our this non-homogeneous equation. This is the particular solution of the non-homogeneous linear equation. But if you want to find the general solution, you still need to find two linearly independent solution for the corresponding homogeneous equation. Okay, that is, you still want to find some function such that the left hand side of the equation becomes 0. But by our previous computation here, we see that if we take k such that the k square, this coefficient k squared minus 3k plus 2 equal to 0. If we take another k, making the k squared minus 3k plus 2 equal to 0, then the corresponding axk will be a solution of our corresponding homogeneous equation. Because although we have axk here, but now we multiply 0 here. So that is when k is 1 or k is 2, we obtain the two solution for the homogeneous equation. That is, y1 is x and y2 is x squared. Therefore, the general solution of this non-homogeneous linear second order variable coefficients equation is c1x plus c2x squared plus x cubed. Okay, so this is a very useful method to solve some particular second order variable linear coefficients equation. Okay, and I also want to remind you that in addition to the method presented here, we also have another method to solve this equation. This equation is x squared minus y double prime plus something x multiply y prime plus a constant y. So this is a special form of Euler equation. Euler equation. Euler equations is always solvable. It can be transformed into a linear second order equation which is constant coefficients. We will have an example later. The Euler equation is a problem in a section of our textbook. Okay. We solve this equation. This equation is also second order linear, non-homogeneous, because the right hand side is minus 2, not 0. But this equation is also variable coefficients. Okay, so how to solve this equation? It seems very, very difficult. And as I said before, for general variable coefficient second order linear equation, we do not have a general method to find the solution. But we can find some particular solution by observation. Okay, for example, here the right hand side is very simple, -2. So here is also -2. On the last term on the left hand side. So if we take y equal to 1, when y equal to 1, the y prime and y double prime are all 0. Therefore, the left hand side, both the left hand side and the right hand side are all -2. So y equal to 1 is a particular solution of this non-homogeneous equation. Okay. And also, this is the most simple solution. But can we find some slightly complicated one? Because all the coefficients are polynomial of x, so we consider x polynomial of x. So we don't want to consider a very higher order the polynomial. For example, we consider the one first order the polynomial, that is y equal to x. How about x? So substituting y equal to x into the equation, then y double prime is 0. So as you can check, y equal to x is also a solution of this non-homogeneous equation. Therefore, capital Y1 is 1, capital Y2 is 2, are all solutions of this non-homogeneous equation. So we already obtained the two solutions of the non-homogeneous equation. But we want to find the general solution. How to find the general solution? To find the general solution, you need to find general solution of the homogeneous equation, or you need to find two linearly independent solution of the homogeneous equation. But how to? We know that we have studied the method of reduction of ordered. A second ordered equation, once you get a solution for the homogeneous equation, the second ordered equation can be transformed into a first order equation, which is solvable. Okay, this is the reduction of order. This is even true for higher order linear equation. Okay, as we have proved a general result on this respect. Okay, so but we don't know which function is a solution of the homogeneous equation. We get two solutions, but both of these two solutions are solutions of the non-homogeneous equation. But we need a solution of the homogeneous equation. How to get the solution of the homogeneous equation? We have a general result. For a given linear differential equation, the difference of two solutions for the equation is a solution of the corresponding homogeneous equation. Okay, this is a result we proved in our previous lecture. Okay, so using this result, the small y1, that is the difference of capital Y2 and the capital Y1, which is x minus 1, is a solution of the homogeneous equation. Okay, then to apply the reduction of order, we want to find solution of this form. The null solution of the homogeneous equation multiplied by some v. We introduce a new unknown function v, whose relation with our unknown function y is this. Okay, so this equation is x minus 1 v. So we in substituting such a function y equal to x minus 1 v into the equation, and we see that to substituting into the equation, we need to compute the derivatives of y. So the first order derivative of y is this. Y prime is v plus x minus 1 v prime. And the y double prime is also computed. Okay, so we're substituting all this into the equation. So this is the 2x minus x squared, the coefficient of y double prime. Now this is our y double prime. Okay, and then the first order term, 2x minus 1 is the coefficient of the y prime. So this is y prime. This is y prime. Finally, minus 2y is 0 because we are considering the homogeneous equation. We want to find the two solution for the homogeneous equation. We already have a small y1. We need to find another one. So we consider the corresponding homogeneous equation by the method of reduction of order. So we get introducing a new unknown function v and substituting into the equation the corresponding homogeneous equation. We get this equality. This equality maybe. Yes. We organize this the left hand side of this equality to collect the coefficient of v double prime and the coefficient of v prime, and in this equation we also has a v, but we don't need to compute the coefficient of v because the coefficient of v must be 0 automatically. This is the spirit of the reduction of order. When you make this transformation of unknown function, the new equation will never contain 0 order term, that is v, 0th order derivative, that is v itself. The new equation will never contain terms involving v. It only contains terms of v prime and v double prime. So to faster our computation, when you organize the left hand side of this equality, you don't need to consider the term involving v. So this term involving v and this term v here and 2x minus 1 multiply this v, we don't need to compute. Actually they already be 0, as you can see immediately. But in some situation maybe it will be, the explanation will be very complicated, but you never need to compute the coefficient of v. So this is the trick. Anyway, we get the new this equation for the new unknown function v. So this is a second order linear equation of v. But the good thing is that this equation does not contain the v. Therefore, we can introduce another new variable u, which is v prime. Then this u will satisfy this first order homogeneous equation, and this equation can be easily solved. And you will find that the solution u is the exponential of this this function, and by direct computation you will see that the u is x minus 2 over x minus 1 square. Okay, so we have to find the derivative of v. So when we integrate this u, we will obtain the v. Then y1 multiplied by v, the correspond, when you integrating u obtain the v, then y1 multiply v is our y solution of the homogeneous equation. So this is the second solution of the homogeneous equation. Let's do this. So we have already obtained our v here. We already have obtained our v here. Then so v is the integral of v, which by direct computation is this fraction. Finally, the second equation is vy1. y1 is x minus 1, therefore y2 is x squared minus x plus 1. So the general solution is C1 y1, that is x minus 1, plus C2 y2 plus 1. 1 is a particular solution of our non-homogeneous equation. 1 is the particular solution. Of course, the 1 you can also use to x. You can also replace the 1 here by x, but that solution is the same as the previous one, which different arbitrary constant C1 and C2. Okay, so actually they represent the same solution of our non-homogeneous equation. Okay. Now next example. Next example is still linear non-homogeneous variable coefficient second order equation. Okay, how to solve this equation? For this equation, we see that the left hand side is y and x multiply y prime and x squared multiply y double prime. Okay, so this is again Euler equation, as I mentioned before. But we can also use the previous method to find the solution of this equation. We want to find y to be some polynomial. polynomial, and the order of the polynomial we want as lower as possible, so that we don't need to consider very many coefficients. So the right hand side is a first order polynomial. Therefore, we also consider solution to be a first order polynomial. We want to see whether we can find suitable AB so that such a function ax plus b is a solution of our equation. Okay. So to do this, we substituting this y into the equation. We obtained 4x minus 3 is the right hand side of the equation, which is equal the result of substituting this y into the left hand side of the equation. Then by the little computation, this can easily be compute. The result is 6b plus 2ax. Therefore, a is 2 and b is minus a half. Therefore, the y is 2x minus 1 over 2. Okay, so this is a particular solution of the no homogeneous equation. Then the homogeneous equation is the Euler equation, as I said before. Okay, so the Euler equation is equation of this form: x squared y double prime plus alpha x y prime plus beta y. So our equation is of this form. For Euler equation, according to the problem in our textbook, I don't remember which section. Every section of our textbook has a set of problems for you to do some exercises. So we have a problem about Euler equation. The method to solve Euler equation we have not discussed previously. So this is the purpose of talking about this example. So the method is to introduce a new variable t. T is the logarithm function of x. That is, x is exponential t. So that is, we make a change of independent variable. Change of independent variable. Previously, our independent variable is x, but now we will use t as a new variable. So we need to express the derivative of y with respect to x by derivative of y with respect to t, because all the x squared in this equation are exponential of t. Okay, so we need to express the derivative of y with respect to x, that is y prime, y double prime here, by derivative of y with respect to the new independent variable t. So how to do this? So dy dx by the chain rule, it is dy dt over dt dx. And dt dx is 1 over x. So dy dx is 1 over x multiplied dy dt. So this is the relation of the first order the derivative of y with respect to x and with respect to t. Okay, we still need to compute the second order the derivative. So second order the derivative of y with respect to x, that is the derivative of the dy dx with respect to x. Again, we apply the chain rule because now dy dx we have just computed. We have just computed dy dx is 1 over x multiplied dy dt. So we need to compute this. To compute this is a multiplication 1 over x multiplied dy dx. So we apply the multiplication law, that is 1 over x multiplied the derivative with respect to x for dy dt, then plus the derivative of 1 over x with respect to x, that is minus 1 over x squared, then dy dt. So this is the multiplication law for derivative. Okay. So here we have dy dt over the derivative of dy dt with respect to x. So this need to transform again. This can be written as dy dt with respect to t, then dt dx. Okay, that is d something dx equals d something dt multiplied dt dx. So this first term, by this law, this first term is transformed into this term. Okay. So, and we copy the second term here, and now this is precisely the second order derivative of y with respect to t. Then dt dx is 1 over x. So in conclusion, this is 1 over x square, the second order derivative of y with respect to t. Then multiply x square 1 over x square dy dt. So this is the expression of the second order derivative of y with respect to x. Okay. Now substituting all this computation into our equation, 4et minus 3 is 4x minus 3, which is x squared, because y is a solution of our equation. So we want the y to be solution of the equation. Therefore, the y satisfies the equation. So we have this equality. Then the second order here, the double prime and prime means derivative with respect to x. But we have represent the derivatives with respect to x by derivative with respect to t. So we substituting the computation here. So that is x squared. Y double prime, that is the second order derivative of y with respect to x. So by this equality, y double prime equals this. Similarly, y prime. So we minus 4x y prime. Y prime is 1 over x dy dt and plus 6y. So the x here cancel, and the x squared here also cancel with the denominator of the two terms in the groups. Okay, so this is precisely y double prime with respect to t minus 5 dy dt plus 6y. So this is a linear second order equation which constant coefficients, no homogeneous. But such an equation is very easy to solve. Okay, so the solution is y equal to this is the solution of the homogeneous equation, and this 2ex minus a half is 2x minus a half. So this particular solution of the non homogeneous equation is obtained. We assume y equal ax plus b and the determinant ab. Okay, so in other words, you to get the general solution of this non-homogeneous equation, you can either solve this homogeneous equation, then using the method of undetermined coefficient to get a particular solution of this non-homogeneous equation. Then the result is this. Then you replace the variable t by our original variable x, you will obtain the final result. This is a method to get the general solution for non-homogeneous equation. You can also replace the left hand side to be 0. Consider the homogeneous equation. Then the general solution of the homogeneous equation is C1 E2t plus C2 E3t. Then you C1 E that is C1 x squared plus C2 x cubed. Then you add the particular solution of the non-homogeneous equation, that is 2x minus a half we obtained previously. So to get the general solution of the original non-homogeneous equation. Okay. So our next example, we are required to draw a direction field of this equation. This is an initial value problem. For first ordered linear equation. So this is a quite easy problem. But we need to draw a direction field and maybe some integral curves. Okay. Then we need to study the behavior of the solution. How solution behave as t becomes large. And the behavior of the solution, does the behavior depend on the choice of the initial value a? If it depends on the initial value a, then the critical value of such a, denoted by a0, So that is, if a greater than a0, the solution will behave, you have some behavior. If a less than a0, the solution will have another behavior. So we need to determine this a0. Okay. So this is the problem. This problem, because it is a graphic problem, we need to draw the direction field. Therefore, we go to apply our homepage, our web page about the software. Okay, so the equation, we need to solve y prime. Y prime is 2y plus expression of minus pi t. Okay, this is the solution. So the y prime is over 3. This is y prime. So we copy the y expression of y prime into our this web page, and we are dy dt. Therefore, we need to replace this by dy dt. Then copy the expression of dy dt into this box. Then enter. So this is the direction field. As we did before, we increase the number of both directions to make a final picture, but 30 is the maximum. You could not be any larger. Okay. So now we move the range of t and y. Here t is minus 4 and 4. Maybe we use minus 0.5 to maybe 10. Maybe 10. We can adjust it as we like. And the y to be minus 1 and maybe 3 is okay. So this is the graph of the direction field. So what should we do? We need to determine whether the behavior of the solution depends on the choice of the initial value. So we take several different initial value. So y 0, a is 1. This is an initial value, and y is minus 1, maybe minus 1. You will see maybe our y will be minus 3. Okay. So you see y is 1. The red curve is the integral curve of the graph of a solution for a initial value a is 1, and the green curve is a equal to minus 1. So you see when a is 1, the solution goes to infinity. It seems that the solution goes to infinity when t large. And when a is minus 1, that is the green curve, it goes to negative infinity. So the behavior is different. So there are many integral curves which different behavior. But we need to find the critical one. How to find the critical one? Critical one is the curve very close to the t-axis, the horizontal axis. So we clear all the curve, and we consider a curve very close to the x-axis. This should be the critical. You compare the red and the green. The red will close to infinity. The green will decay to negative infinity. Okay. So this curve, they are almost coincide at the beginning near t equal to 0. So the y coordinate of the intersection of the curve, which the y-axis, that is, you can read the coordinate from the left lower corner of this page. Okay, so you will see that the number is the y coordinate of the intersection of the curve which the vertical axis is minus 0.12415. Of course, this is not very accuracy. Maybe so minus 0.13. So you can find this is an approximate value of the number. So we believe when a is greater than this number, the curve will close to positive infinity. When a is negative to this number, the curve will decay to negative infinity. Okay, so therefore the curve very close to the x-axis, the intersection of the curve with the y-axis, the y-coordinate, that is minus 0.12415 is the critical value. Okay, so we have solved this problem by drawing the direction field and the integral curve using our web page. Okay, and of course we are required to solve the equation and find the exact value of the critical value A0. We obtain the minus 0.13 and something, and that is an approximate value, not exact value. Okay, so to get the exact value of the A0, the only way is to solve the equation and by some analytic computation. Okay, so this is easy. The solution of the equation, because this is the first order linear equation, the solution can be obtained by integral. Okay, so simplify this, computing the integral, and then you will get this y. So how to determine which a is the critical value? So when t goes, this term is when t goes to positive infinity, this term, exponential term at the beginning, increase to positive infinity. But the other part of this solution, that is this part, we don't know whether this part is positive or negative. But when t large, this exponential is minus exponential. So when t goes to positive infinity, this term goes to 0. Therefore, the critical A should make the limit of this to be 0. If a greater than that value, this part will be positive. The limit of this will be positive, and y goes to positive infinity. Well, if this part is negative, then y will go to negative infinity. So the critical value A0 satisfies the limit is 0. The limit is 0. That is exactly this equation. Because this term, the limit of this term is 0. Okay. So this tell us how to determine the solution, the condition for the critical value A. That is, it must be a solution of this equation. So this equation, this is the exact value of A. And if you compute the value numerically, that is minus 0.14898. Okay, but our previous observation by picture is minus almost the same. Okay, but you could not expect that you can get the value from the picture, the accurate value from the picture. This is you could not expect this. But anyway, we can determine the value either by either graphically or analytically. Of course, the result obtained analytically is accuracy. Okay. Okay, this is this picture. This example. Now, next we consider. We go back to the technique of solving differential equations. Okay, here is an equation: y double prime plus ty prime square is 0. Although this equation is very simple, but this equation is a nonlinear equation. Nonlinear, because the derivative of y has a square here. So this is a nonlinear equation. Nonlinear equation usually will be much difficult than linear ones. Okay, and in particular the second order and higher order nonlinear equation. We can solve many nonlinear first order equation. But when the order is 2 or higher, it's difficult to find a solution. But for some particular form of nonlinear equation, we can have some technique to find the solution. Okay, here this class of equation is missing dependent variable. Dependent variable is y. Independent variable is t. So this equation, we do not have y in this equation. More generally, for second order equation without y, it only contains y, the derivative of y and the second order derivative. For such equation, we can always transform the equation into a first order equation and try to solve it. Okay, so the technique is to introduce a new unknown function, v. We set v to be the derivative of y. Then the first order derivative of v is y double prime. Okay, therefore the equation becomes first order ODE, that is v prime equal ftv. This is a first order ODE. If we can solve this ODE, then the maybe I did something wrong. Okay, if we can solve this ODE and find v, after integrate v, we will obtain our solution y. Okay, because v is the derivative of y. Therefore, we solve the equation. So for our equation, we use this technique. Set v equal to y prime, then v prime is y double prime. So our equation, the equation we want to solve becomes v prime plus tv square is 0. This equation is a first order nonlinear equation, but the equation is separable. We grouped the v on the left hand side and the t on the right hand side, and then integral both sides. We obtained the left hand side, the antiderivative of left hand side is 1 over v, and the antiderivative of the right hand side is half of t square plus a constant c1. That is, v is half of t square, v is 1 over half of t square plus a constant. Then we can simplify this v to be 2 t square plus c1. And our y is the integral of this v. Note that our v already contains arbitrary constant. After integrating v, we will obtain another arbitrary constant. Therefore, the resulting y will contain 2 arbitrary constants. One is c1 contained in v, the other is c2. Okay, so our equation is a second order equation. The general solution should contain 2 arbitrary constants. Therefore, our y will contain 2 value arbitrary constant is reasonable. Okay, but this integration, the method to compute this integration depends on the sign of c1. C1 is using the initial value condition. V is y prime. Therefore, let t equal to 0 in this the expression of v. We will see that c1 is 2 over v0. That is 2 over y prime 0. So the sign of c1 depends on the initial value condition. If y prime 0 is positive, then c1 is positive. If y prime 0 is negative, then c1 is negative. And if y prime y prime 0 could not be 0. Okay, then depending on c1 is positive or negative, you can compute this integral, this antiderivative. Okay, so we will not continue our computation. So this is the method to solve equation, second order equation without the dependent variable, without y, only y double prime, y prime, and t. So you make this transformation, introducing a new variable v, you will solve the equation. Okay. So our next example, still nonlinear equation. Y double prime plus y prime square equals 0. So the method we developed in this example, missing dependent variable could not apply. Because missing dependent variable means that y does not appear in the equation. Okay, but now our equation we have a y here. Okay, but in this equation we do not have independent variable t. There's no t in this equation. In our previous example, we do not have y, but we have t. So this is the difference of these two classes of solvable second order equation. Okay, so how to solve this class of equation? Missing independent variable, no t, but we have y. How to do this? The general form of this class of equation is y double prime equal fy y prime. Then we introduce a new variable v to be y prime. So when we set v to be y prime, then y double prime will be the derivative of v with respect to the independent variable t. Okay, then dv dt, we can write dv dt using the chain law by dv dy multiplied dy dt. And dv dy, dy dt is y prime. Here, dy dt is y prime. Y prime is v. So this is v dv dy. Okay. So the second order derivative of y with respect to t equals v multiplied the derivative of v with respect to y. Okay. So the equation becomes this first ordered equation, which y be independent variable and v to be the dependent variable. So this is the first order equation. We have many methods to solve it. Okay. Then after we solve this equation, obtain y, obtain the relation of v and y. So that is then using v equal y prime, we will obtain the solution y. Okay. Now we apply this idea to solve our equation here. Okay. So for our equation, y double prime is v dv dy. Therefore, y double prime on the left hand side is y v dv dy plus y prime square, that is v square, is 0. So this equation is contains both terms on the left hand side contain v. We want to cancel this v, but when v is 0, you could not divide it by v, but by v on both sides. So the case v equal to 0 need to be considered separately. So we assume that v is not 0, then we can cancel the v to simplify the equation into this equation y dv dy equal minus v. This is separable. Therefore, it is easy to solve this equation to get v equals C1 y. So v is y prime. Therefore, C1 is Vy, that is y prime. Y prime is half of the derivative of y square. So the derivative of y square is 2c. So y square is C1t plus C2. So this is the solution of our nonlinear equation, of the equation we want to solve. Okay. Of course, this equation is this solution is an implicit solution because we do not have y equal to something. Instead, we have an equation containing t and y, which determined y as a function of t. Implicitly determined y as a function of t. This function is the solution of our equation. Okay. So this is a solution. Now we go back to the case v equal to 0. This case we have not considered because our argument before only apply to the case v is not 0. Then we obtain the y square equals C1t plus C2. Okay, but if y is 0, that is y prime is 0, so y is c. Y is c, that is constant, is also a solution. Okay, so go back to the equation, you will see that for any c, for any constant c, y equal to c is indeed a solution. But that solution, this particular solution, is also contained in our general solution. You take C1 equal to 0, then you obtain the constant solution. Okay, so our final expression, our final implicitly given solution contains all the solution of our original equation. Okay. Next, we consider this example. This is x squared y double prime plus xy prime minus y is 0. So this equation is also an Euler equation. Sorry, maybe not. Yes, it is Euler equation, but it is also the so-called exact equations. We know that for first order equation, m plus n dy dx dt equals 0. that kind of equation we have exact or not exact. If the equation is not exact, we can find an integrating factor to transform into an exact first order equation and solve it. Okay, for first order equation we have exact equation and a not exact equation. For second order equation we can still have the concept of exact equation, which is a problem in the second section of chapter 3 in our textbook. You can check the problem and to see the result about second order the exact equation. Then as the application of the method introduced in that problem, you are required to solve this equation. Okay, so this equation can be solved using that method. But now we want to solve this equation more easily. The reason is that the equation is somewhat special. It is x squared multiplied y double prime plus xy prime minus y. So we see that if y is something multiplied xk, if y is a power function, then if y is xk, then y prime is x k minus 1. But you multiply x, that will also xk. Similarly, x squared y double prime is also xk. Therefore, it is possible that this equation has a solution of the form y equal to axk. Okay, so we want to find solution of this form. Because of course the a here is not necessary, because this is a homogeneous equation. For homogeneous equation, if for some a this is the solution, then for any a the corresponding y is also the solution. Okay, so this a is not necessary. Anyway, we substituting this y into the equation, we will obtain by direct computation. This will be axk k squared minus 1. So to make this to be 0, of course you can take a to be 0. A is 0, give us the y equal to 0. The 0 solution, that is not interesting to us, not helpful. But here we have k squared minus 1. So we let k, so that k squared minus 1 is 0. So k is positive and negative 1. Okay, so for k equal to 1 or minus 1, y equal to xk is a solution. So we get two different solutions. So the general solution is the linear combination of x corresponding to k equal to 1 and the inverse of x, which is corresponding to k equal to minus 1. So this is a simple method to solving this equation. So this equation, we have three methods to solve it. Firstly, it is an exact equation. You can use the method in this problem in section 2 in chapter 3. And the third method is the second method is that this is an ODE equation. You can use the method of ODE equation we presented to you in the previous example. Okay. Also, you can use this method trying to find solution of a particular form, which is unknown coefficients and unknown parameters, and then using the equation to determine the unknown parameters. Okay, so to solve second order linear equation with variable coefficients, we do not have a general method, but for a particular equation, we will have a particular method. Some equation can be solved by many different ways. Okay, so this is an important example. Next example, this is a theoretical result that we mentioned in our lecture and also in the textbook, but we have not proved this result. Since this is quite important, so we need to have a look on it. Actually, this example is a problem in section 2 of chapter 4. Okay, so L is an unordered linear differential operator. I from 0 to n, ai multiplied the ith ordered derivative of y. Okay, so for this linear differential operator, we have a characteristic polynomial that is replacing the ith ordered derivative of y by r. R is variable ri, okay, power function ri. So this is an nth ordered polynomial which is called the characteristic polynomial of our linear differential operator. So if R0 is a root of this characteristic polynomial, that is R0 is 0, and the multiplicity is S, then the conclusion is that x e lambda 0 t, t e lambda 0 t until t s minus 1 e lambda 0 t are all solutions of the homogeneous nth ordered linear equation. This is the conclusion, a very important conclusion. This is the theoretic foundation of our method, our algebraic method to solve any given nth ordered linear differential equation which constant coefficients. Here the ai are constant, are real numbers. Okay. So how to prove this result? This result is a problem in the textbook, and it has split the argument by 2 or 3 steps so that you can easily solve it. But since we have completed this part for a while, and I need you to master the proof of this important result. So if you have tried the problem in the textbook, maybe you find some difficulty. And anyway, I hope that our discussion later, the below discussion will help you to understand this important result. Okay, so R0 is a root of multiplicity S. So from this assumption, we know that R0 equal 0 and prime R0 equal 0 until the s minus 1, the ordered derivative of z at 0 are all 0. But since the multiplicity is s, the s ordered derivative is not 0. So this conclusion comes from the assumption that R0 is a root of multiplicity s. Okay. Now, how to prove the result? How to prove this result? According to the hints given in the textbook, we for convenience, we introduce this two variable function rt. We consider the function exponential of rt. Here r is change and t is change. Therefore, this is the function of two variable. So we denote it by f. Then for any k, for any non-negative integer, the case ordered derivative of L E RT, the differential operator acting on this function, you will obtain a new function. This function is a function of t, but because this function ERT contains a parameter r, this function LERT, although you may mainly consider this as a function of t, but it also depends on r. Therefore, this is actually a function of rt, a two-variable function. So this is the case-ordered derivative of this two-variable function, which respect to the variable r. How to compute this? So LERT is the linear combination of the ith-ordered derivative of ERT. This part, this fraction is the ith-ordered derivative of ERT. Then multiply by AI and sum up. So this summation, this sigma summation, give us LERT. And we need to take the case-ordered derivative which is respect to r. Okay. So, but this fraction is the derivative which respect to t to I times. So ERT is FRT. Therefore, this fraction can be written as the ith-ordered derivative which is respect to t for our FRT, that is ERT. Okay, and since the taking derivative is a linear operation, so multiplying by a constant AI and sum up and take derivative can switch. Firstly, taking the derivative, then multiply AI, then sum up. Okay, so we can move the partial derivative with respect to R inside the summation, even inside the coefficient AI to get this result. Then these two derivative can be switched by the result from multivariable calculus. I don't know whether you have learned the theorem from your currently calculus 2 course. I don't know, but in that course you will have a result that firstly taking derivative with respect to t and then with respect to r, the order can be switched. Switched by firstly taking derivative with respect to r and then t. This step is apply the result in calculus. The switchable property of missing derivatives. First derivative with t and then r equal first r and then t. Okay. Now let's have a look on this. This is the case ordered derivative of FRT with respect to r. So that is ERT taking derivative with respect to r k times. Okay. Then this result is tk. First order derivative of ERT which r is TERT. Take derivative with respect to r again, you will get another t, therefore is t squared. And taking derivative with respect to r k times, you will get kt. Multiplying the kt's, you will get the power function tk here. And then that is this fraction. This fraction is equal to this. So our result is this. Our result is sigma ai di dt I. That is the derivative which is respect to t I times. Okay. The derivative which is respect to r k times already disappear because the result already we already figure out the result. So the derivative operation is complete. Therefore, it will not appear in our last result. But this last result, consider this as a function of t. Then this is precisely a function of t, the ith order derivative of a function of t, multiply ai and then sum up. Therefore, this is precisely LTKERT. Sorry, here is a code mistake. So you don't want to see the pause here. Anyway, we obtained this result. The case ordered derivative of LERT equals our linear differential operator L acting on TKERT. Okay, so these three lines explain this equality. On the other hand, our LERT, by definition of L, is AI multiplied the ith ordered derivative with respect to t of the function ERT, then sum up. But this derivative is this derivative equals RIERT. So this is AIRIERT. And this sum, because the ERT does not depend on the summation index I, so you can move the ERT out and obtain this. And the summation here is precisely our characteristic polynomial, ZR. So we get this result. LERT equal ERT ZR. So we compute the derivative. Previously, we already computed the derivative of LERT with respect to RK times. Now we use the result is LTKERT. This is the one hand. On the other hand, we have this equality. This equality is we are very quite familiar with this equality. So we can also compute the same quantity. The case ordered derivative of LERT with respect to R. Using this result, that is this. So how to compute the case ordered derivative of this? So because we are derivating with respect to R, we can consider T as a constant. So this is ERT is a function of R. ZR is also a function of R. Therefore, this is precisely the case ordered derivative of the multiplication of two functions. So from calculus, we have a Leibniz law. We already used Leibniz law in our previous lectures. Okay, so to use the Leibniz law, this derivative is the sum I from 0 to k. Here is the number of combination ki. Okay, then ERT, the k minus I ordered derivative of ERT multiplied the ith ordered derivative of R. Okay, so this we get this equality. So these two results should equal. Okay, so so this result can be written further. Further is that the k minus I ordered derivative of ERT could be computed. Because our derivative is with respect to R, therefore this will have maybe I have making some mistake. Our derivative is with respect to R, so this should be T, not R. Sorry, I make a mistake. I thought that the derivative is with respect to T. Therefore, every derivative of ERT will give us an R. Therefore, that is R k minus I. But actually, the derivative is with respect to R. So every derivative will give us a T. So this should be T k minus I. Okay, so this is a misprint, mistake. So so we get this result. This is the final result. This is another way to compute LERT. Okay, sorry, not LERT. This is another way to compute the case ordered derivative with respect to R for LERT. And we also have another expression of the same quantity, which is TKERT. So these two, the last line in this page and the yellow box, the term should equal. Okay, so they are equal. That is, we have this equality. So using this equality, we're evaluating this equality. This equality is true for every R and every T. But this is true for every R and every T. We take R to be R0, the root of the characteristic polynomial of multiplicity S. So that is Z R0 equal Z S minus 1 R0 are all 0. So if K is less than S, if K is at most S minus 1, then in this equality, we take R to be R0. Then since I is less than K, I is not greater than K, and K is less than S, and once K is less than S, since in this summation, I is not greater than K, and K is less than S, therefore all the I here are less than S, at most S minus 1. Since R0 is the root of Z of multiplicity S, that is, all this is 0, all these are 0. So for every term for I is 0, I is 1, I is 2, and I is K, all the Z, I's ordered derivative of Z at R0 is 0. So this is 0. The right hand side is 0. So we conclude that the result is 0. That is, LTK ER0T is 0. So this proves that for K less than S, that is, K is 0, K is 1, K is 2, until K is S minus 1, the TK ER0T makes L acting on this function is 0. So this function is a solution of Ly equal to 0. So this proves our result. Okay, so this is 0 for K less than K less than S. How about K equal to S? So K is 0, K is 1, K is 2, until K is S minus 1, the result are all 0. How about when K is 0 S? When K is S, When k is s, because so when k is s, therefore this summation will contain I equal to s. If k is s, then the last term of this summation is I equal to s. But I equal to s, this is not zero. The previous term I from 0 to s minus 1 are 0, but the term I equal to s is not 0. So we conclude that Ts L Ts E R0 T is not 0. So Ts E R0 T is not a solution of the homogeneous equation. Okay?